well, good morning, everyone. I know it's bright and early on Saturday, so I know it can be a little bit challenging, but I do appreciate you guys taking the time to come out here and listen to what I have to say about solar cycle predictions. So let's start by waking you up with a question. Why do we care about solar cycle predictions? Come on. Solar storms, yeah. And why are solar storms important? I'm sorry? Satellites, yeah. Solar storms can impact the Earth's atmosphere. They can cause additional drag on the satellites. And when you're spending billions of dollars putting these satellites up in space, you want to make sure that they don't come crashing down to the Earth. Any other reasons? Astronauts, exactly. We've got these assets in space. We're wanting to send people up into space. At the International Space Station, we've got astronauts always up there. And if a large CME comes blasting towards them, we want to give them the opportunity to be as safe as possible. If we're sitting here talking about planning a mission to Mars. This is going to put the astronauts into the heliospheric environment for many years consecutively. And so we want to be aware of what kind of conditions we're going to expose them to. So I've got a list here, right up there at the top, threats to astronauts in space, satellites, either by a direct hit from a CME or, changing their orbits can have a significant impact. They, as I mentioned, the trip to Mars.
Meaning about apparently that.
Okay.
Sorry about that.
Let's see here. Is that better? Okay, good. Sorry about that. Galactic cosmic rays are inversely proportional to the solar activity cycle, and so we want to take that into consideration. Solar storms could have an impact on our GPS satellites, communications. Space weather can impact radio communications. And in case of an extreme solar storm, it can actually impact our power grids. Back in 1986, there was a huge solar storm that actually disrupted the power grids in Quebec, Canada, for, I believe they were out of power for about a week, and this was sometime in March, so I imagine it was quite cold and very uncomfortable for the people that were there. And in addition, it can change, have impacts on our atmosphere, changes in the ozone. Some have suggested that it might have an impact on clouds, although that is a little bit debated. And there are even others that point to a relationship between the solar activity cycle and climate, although I think that's actually a very, very, very small factor. It is a very small component of the climate change that we're experiencing. So I wouldn't put too much weight on that. But more importantly, it gives us an opportunity to get a greater understanding and scientific knowledge about dynamo mechanisms and the context of the sun as other stars as we explore the rest of the galaxy and we want to learn more about other stars. The sun gives us a great opportunity to kind of explore the parameter space on a much closer environment. So what do we even know about solar cycles? What can you guys tell me about a solar cycle? What do you know? $11 years, yeah? Anything else? Yeah, it can rise fast and decay slowly. A little bit of it depends on the shape of the cycle. Weaker cycles have a much flatter top, but they do tend to have these fast rise and slow decays. Anything else? Yeah? Yeah, there's polar field reversal. Yeah. So there's been a little bit of recent work that's really challenging our basic understanding of what the solar activity cycle looks like. There's work by Hoyt, Shatton, Klett, and Svalgaard. They've been recently going back and digging into the historical records, and they're finding evidence that our traditional picture of the solar activity cycle may not be as firm as we had actually initially thought. In particular, this has impacts on the concept of the modern maximum. There's been generally a thought that in the last few cycles have been much, much stronger than historic cycles. And this latest sunspot information is starting to tell us that, well, maybe this maxima isn't entirely all that unusual. But also in terms of the Maunder Minimum. In the past, people had thought that the Maunder Minimum, if you see the red curve, that's the old sunspot number curve. And the Maunder Minimum looked like pretty much a step function. All of a sudden, the sun stopped working altogether, and then magically 80 years later, it started up again. But with the new curve, we kind of see that, well, maybe it's a much more of a gradual process. It wasn't so much that the sun just stopped cycling altogether. It just went into this weaker mode or phase of operation before slowly recovering. And so this is kind of challenging our concept of what a normal cycle even looks like. But fortunately, we have a fairly, yeah, go ahead. Well, a lot of it is going back and really taking a closer look at the historical records and how people went about calibrating. Actually, Leif Svalgaard was here this week, and he gave a great talk yesterday talking about some of the efforts that he's been doing. But a lot of it has to do with, there was, as the traditional measure of the sunspot cycle for the most longest consistent period of time was the Royal Greenwich Observatory. And evidently there was, kind of a learning curve when Royal Greenwich started counting sunspots. Sunspot counting is actually not as simple of a process as you might think, in particular when you're counting it in terms of group sunspot number, because then you got to get into what is actually one group, and then you get active regions that are dispersing, and then you've got their shear, and so they're getting spread apart, and so this active region kind of might look like it's part of this active region, and so actually getting a hard count is challenging. But also going back to those historical records, there wasn't always as much consistency. There was one case where there was one observer, the basis of the sunspot number for that year was a simple statement. I did not observe any sunspots this year. And so they just put zeros in for all the values there. And this guy was living in England. And so even if he had, optimal conditions, you gotta imagine that there was probably a lot of cloudy days there. Maybe he wasn't as diligent as he could have been. And so, it's a bit of taking for granted, how much faith we're putting in these measurements. So what they've done is they've gone back and tried to comb through the data, find additional observers, and try to get a better consensus of what those observations actually look like those many, many, many years ago, which is no small task when you're talking about observations that occurred, 400 years ago. Digging up history can be a little bit challenging. But it is interesting to note that this is kind of something in the works, and there's not even, at this point, there's not even a consensus right now. So this is something that's kind of being actively debated in our community right now as far as what the historical record 400 years ago, 300 years ago looked like. But the good news is we have fairly good records for the last couple hundred years, the last 24 cycles. And what these tell us is that the activity on the sun is periodic with, as you mentioned, an average period of about 11 years and a peak sunspot number on the order of about 100. We see, let's see, do I have a pointer up here? Oh, there it is. Okay. We see some general trends. So this is the magnetic butterfly diagram. I'm sure you've seen that many times already this week. But we see some general trends. The active regions tend to appear at high latitudes and progress more equatorward as the solar cycle progresses. There's typically an overlap of about 2 years between one cycle and the next. Although this most recent cycle minimum, we didn't really see that. We had this long extended minimum that didn't really express that characteristic. So I mean, to a crude approximation, we could almost treat the solar cycle history as a time series and do some crude approximations to make an estimate of what the next solar cycle might be. We might do something like, just let's assume that the next cycle is going to be about what the average cycle is, which means that every cycle is going to be about 100. And if you look at the histories, most of them didn't really exactly fall on 100. There's a lot of fluctuations in there, so this isn't a very good approximation. We could assume that the next cycle is going to be just like the cycle that we just had. But we see that also fails. You know, in the case in point here, cycle 23 to cycle 24, we would have gotten a vastly wrong answer there if we had made that assumption. There's also been attempts to do wave analysis of the periodicity in the sunspot cycle, but that isn't always very effective either. Case in point here, they might do a wave analysis here going from 19 to 20. It would be really difficult to get that big jump in solar activity there. So what I want to talk about today is how we can do better. And what it basically boils down to is that we really need to bring in the physics in order to get a real understanding of how solar cycles work and how to predict them. We really have to bring in the physics. I guess the most ubiquitous thing about the sunspot cycle, or the most important thing about the sunspot cycle, is that it's actually magnetic in nature. And this has really huge impact on how the solar cycle evolves. And so let's take a closer look at that. We know that sunspots emerge with a characteristic tilt called Joy's law tilt. They progress towards the equator as the solar cycle progresses. The polar fields of those active regions are such that as their remnants are transported to the poles, they reverse the polar fields at about the time of solar cycle minimum, forming a weak dipole. In addition to the large-scale active regions, this dipole is like on the order of about the size of one active region. So it's only a small fraction of the magnetic field from those active regions that's being transported to the poles. So back in the 1960s, Babcock was looking at this magnetic nature of the sun, and he came up with this phenomenological model or idea to explain the processes that he saw. So his concept was based purely on the observations, and what he said occurred was that there was the sun started with a dipolar magnetic field. That dipolar magnetic field is threaded through the interior. As you know, the sun has a differential rotation, so that differential rotation will wind up that dipolar magnetic field that's in the interior, causing it to stretch and become stronger. As the magnetic field becomes stronger, it becomes magnetically, it becomes buoyant, and it rises up to the surface, producing active regions with the characteristic Hale's polarity and Joy's law tilt. Those active regions are then shredded by the turbulent convective motions, and the remnants of those active regions are transported poleward, but in such a way that there's a tendency for the leading polarities to be canceled with the new emerging active regions and eventually across the equator. And so it's preferentially the following polarity that's transported to the poles, which reverses the polar field and builds up the polar fields of the next cycle. We can really break this down into two fundamental processes. The conversion of the poloidal field to the toroidal, and which occurs in the interior, and then the conversion of the toroidal field to the toroidal field to the poloidal field. And we can see this if we draw nice little lines on the magnetic butterfly diagram. We can see that there's these clear, distinct phases of the solar cycle. This is a largely toroidal phase, and this is a primarily poloidal phase, and the sun has this nice oscillation between these two phases. So now that we have a little bit of a better understanding of how the magnetism is working in the sun, we want to think about how we can simulate these solar activity cycles. But there's a lot of things that we need to take into consideration when we do this, because there's a lot of modulation in the dynamo process. And I'm going to just discuss some of these in a little bit more detail. There's the Lorentz Force, there's stochastic processes, and then there's a big question as far as what do we really know about the interior? A lot of what's going on is happening in the interior. These are where the more stochastic processes are occurring. And we're only just recently, with the advent of helioseismology, really getting a chance to see what's going on in there. So let's take a look at some of these ways that the solar cycle can be modulated. The first, of course, is the Lorentz Force. This is that J cross B term. It basically is a back reaction on the flows from the interaction between the magnetic field and the current. And basically what this does is it produces perturbations on the mean flows. The differential rotations, it causes what's known as the torsional oscillations. You can see here. So basically what's plotted here is you've got the differential rotation, which is a fairly steady flow plotted, but then you take out the average fields. And so this is just the difference between the average meridional flow, or the average differential rotation, and the small fluctuations about it. And so this is a really good way of looking at the Lorentz forces coming in. And you see there's these nice patterns that emerge. You've got a poleward component. You've got the motion from the poles to the equator. But then you can also do this with the meridional flow. And when you do it with the meridional flow, you see that there tends to be a kind of a weakening around the active regions. It's like the magnetic field is quenching the velocity. It's reducing the velocity field near those active regions. And so this can cause some modulation in the dynamo mechanisms. And this is important because the meridional flow is basically the means of modulating a solar cycle. So by weakening the meridional flow, you're shortening, by weakening the meridional flow, you're shortening the time it takes for the magnetic field to be transported to the poles into the interior, reducing this flow here. So this has historically been the standard picture of what the meridional flow looks like. You've got this big unicellular, or single cell going poleward at the surface and down into the equator. But the problem is that the meridional flow is a very weak signal. It's been very, very challenging to measure the meridional flow. Even at the surface, where we've got really good observations, it's been challenging to get a handle on what this velocity is. To give you a little bit of perspective, the meridional flow is on the order of 10, 15, maybe on its really good day, 20 meters per second. Compared to the other flows, the differential rotation, where you've got a delta of about 300 to 500 meters per second, or the convective flows, which can be, the small scale convective flows can be thousands of meters per second. And so you've got this very, very weak meridional flow superimposed onto these very fast flows. And trying to get a grasp of what this flow is a little bit like trying to measure the speed of a fly that's on a race car. So you've got this race car zooming by, and you want to measure how much that fly is moving. And so it's not such an easy task. But as I said, we recently had a lot of advances in helioseismology that's given us a chance to look a little bit deeper into the sun and get a better understanding. And it's really been challenging some of the fundamental ideas of what the meridional flow looks like. So as I mentioned, in the past, historically, the dynamo models have suggested it was a single cell, possibly a second cell in the rate at the higher latitudes going counterclockwise. But the recent observations from helioseismology are telling us that really the meridional flow structure is not quite so simple. There's overwhelming evidence that there's actually multiple cells in radius with a very shallow meridional return flow. And so this can have a huge impact on how these dynamo models function. We also have modulations that are due to stochastic forcing. So a lot of this is basically stochasticity that's arising from the very turbulent motions of convection. Convection is just a huge force. Convection in and of itself can create small-scale magnetic fields. It can cause, as we discussed earlier, it can cause fluctuations in the mean flows. It's the process by which it's thought that magnetic flux rope at the base of the convection zone is destabilized so that it can rise, become buoyant and rise up. This is the source of the large scatter that we see in Joy's law tilt. We kind of take Joy's law as a hard constraint, but there's actually, if you haven't looked at the plots, you should. There's a considerable scatter about Joy's law, a lot of variability, and this comes from the convective, turbulent convective motions. It can cause long timescale modulations in solar cycles, and it's thought that it can be one source of solar cycle intermittency, or in other words, periods where we have long extended minimum, and how do we recover from that? And so this is one process by doing that through the stochastic, the modulation due to stochastic forcing. Typically in dynamo models, it typically has the effect of increasing the amplitude and the duration of the cycles. But that's kind of a little bit backwards, because if we look at the solar cycles, we find that if we increase the amplitude of a solar cycle, its duration is actually much shorter. So we see that there's an inconsistency just even in that parameter there. Even getting an understanding of what the convection cells look like inside the sun has been challenging. In the past, it was thought that the convective velocities in the interior were on the orders of close to 100 meters per second, or this is one of the values that's been used in dynamo models. But there's evidence that maybe helioseismology is telling us that there's this observational limit, that it can't be faster than about 10 meters per second. Even the structure of what the convection cells look like is in question. We talked about these Bussy columns, but then the latest observations are not really seeing any kind of indication of them. We're tending to see these long extended structures in longitude, not really latitude at the equator. And so this really drives home the point that our fundamental understanding of the interior is real, or how convection works isn't really very solid right now. Traditionally, it was thought that active regions were formed at the base of the convection zone. They're anchored down at the tachocline, and so we have a small instability that will cause them to rise up. But there's a new theory coming into play where it's thought that maybe active regions aren't formed at the base of the convection zone. Maybe they're formed somewhere in the interior. And what, are they rooted where they're formed, or can they break off and rise up to and basically be just a surface phenomena? So these are some of the questions that we really want to answer in the next few years. Even something as simple as the fluctuations in Joy's law tilt can have a huge impact on how a dynamo model works. This is a work by Mark Misch and Vidya Karak. They've submitted this for publication. But they're showing here that you could take a dynamo simulation that has very regular, very steady cycles, and just by introducing that variability that we see in Joy's law, we get a much different picture of what the solar cycle looks like. We get these rises and falls that we actually see in observation. And so this could be hinting at that there's something intrinsically important with the Joy's law variation. So, predicting long-term trends in cycles, dynamos can do a good job of telling us a little bit more about the physics of solar cycles, how they progress. But how well can we do at just predicting one cycle ahead? So let's take a step back and look at that. So I want to talk to you about a tale of two models, and I think Nick may have given away the punchline. He mentioned yesterday that he was quite disparaging about solar cycle prediction, and he's right. Predictions for solar cycle 24 were all over the board. This is just a sample case of two dynamo models. They're basically the same kind of dynamo models. They're both Babcock Leighton dynamo models. They used essentially the same flow, same differential rotation, same diffusivity, same meridional flows. The biggest difference between the two of them was how they brought in the poloidal source term. Dick Patty used the active regions, whereas Chowdhury did a data simulation process where he directly brought in the polar fields from Wilcox Solar Observatory. And even though the models were pretty much operating in the same sort of fashion, they got very different answers. Dick Patty said Sunspot Cycle 24 was going to be 150 to 180. It's going to be the biggest cycle we've seen ever. Whereas Chowdhury said, oh, no, it's going to be a really weak minimal cycle. And these aren't even the large extremes. If you go look, there's a paper by Dean Pesnell, 2012, where he went out and he found all of the predictions for solar cycle 24, and they ran the gamut. I mean, everything from, oh, we're 10 or 20, sunspots, up to 200 sunspots. I mean, it was a very vast difference between all of these predictions, and it wasn't like they were clustered on one end or the other. I mean, they just really spanned the parameter space there, and so at that time we really didn't have a good understanding of what solar cycle prediction was. So all of this goes to show that despite the successes of dynamo modeling, there's still a lot of challenges to face. Dynamo modeling is hard, especially when the biggest part of dynamo models is happening on the interior, and this is a place observationally where we're not really very well constrained. There's a lot of free parameters floating around, and so even doing something as simple as predicting the next cycle can be very challenging. So what other options do we have? Well, back in the late 70s, Ken Shatton theorized that, we've got this poloidal to toroidal and toroidal to poloidal kind of relationship. And most of the stochasticity is coming in the conversion of the toroidal to the poloidal. So maybe we can have maybe there's a nice relationship. Maybe we can use the polar field strengths as a predictor of the strength of the next cycle. And if you look here, it looks like this is a very reasonable thing to say. I mean, we look at the polar field strengths at solar cycle minimum, and you've got a strong polar field here and a pretty strong cycle. A little bit weaker, a little bit weaker, a little bit weaker, a little bit weaker. It looks like this is a pretty nice correlation. And again, this comes back to the fact that the conversion from poloidal field to toroidal field is a linear process. Yes, there's some minor fluctuations that come in here, but generally it's a linear process. A lot of the stochastic effects that we're seeing in the dynamo mechanism actually occur in the changing of the toroidal field to the poloidal field. And if we look, we can see that back in 1978, no, that's the wrong year. Back in 2000, I think it was 2006, Leif Svalgaard actually used this idea. So don't trust that, that's wrong. But Leif Svalgaard used this idea, and he said, Sunspot Cycle 24 is going to be the weakest cycle in 100 years. And lo and behold, this was correct. Cycle 24 has turned out to be one of the weakest cycles that we've seen in 100 years. And so this idea that the polar field strengths at solar cycle minimum are a good predictor of the next cycles is turning out to be pretty robust. We have additional results. These are results by Andreas Munoz-Jaramillo. He was a student a while back, and he's been a lecturer here as well. But he did this nice work where he went and he used polar faculae as a proxy for the polar magnetic fields. And he found that there's this very, very strong relationship between the polar field strength, the axial dipole, and the amplitude of the next sunspot cycle. And so this is really promising. So the question is, this is great. If we wait around to solar cycle minimum, we can tell you what the next solar cycle is going to be. But can we do better than that? Can we determine what the polar field strength is going to be ahead of time and get a prediction of what the next cycle will be ahead of time? Can we extend that prediction? And so the answer to this lies in this question. How long does it take the flux that emerges in the active regions to be transported from the low latitudes up to the poles? So I've got some numbers here. This is the radius of the sun. Meridional flow speed is about 15 meters per second. Give me a back of the napkin calculation. How long does it take for that flux? Say it starts at the equator and we want to go all the way up to the poles. I'll give you a few minutes to try to work through that real quick. Got a calculator, IDL, Excel. Just an estimate in days or years, either one is fine. Anybody got a number yet? About a year? Okay. Here's my back of the napkin, or actually IDL command line, real quick calculation. Got the radius of the sun here. We calculate the diameter, and we want about a quarter of the diameter to be one hemisphere going from the equator to the poles. Our flow speed is about 15 meters per second. Let's just do a nice conversion to convert this from seconds into days. And I get 842 days. So somewhere between 2 to 3 years. 2 to 3 years it takes the magnetic field. And this is assuming that the meridional flow all over the sun is 15 meters a second. In actuality, this is what it peaks at. You know, it's a profile that rises, peaks at the mid-latitudes, and then falls off as it goes to the equator. So about 2 to 3 years is how long it takes the magnetic flux from those low active regions to reach the poles. And so what can we do with this? Let's simplify our dynamo equation. Let's get rid of all that interior stuff that's really complicated, all these stochastic processes that we don't really fully understand. And let's just look at the surface. Let's look at how the magnetic field behaves on the surface. And so if we do this, we can simplify the induction equation in this way. We're going to say that we're just going to assume that the magnetic field at the surface is radial. It's frozen into the plasma, and it's going to be transported around like passive scalars, floating around in a fluid by this velocity, by the horizontal velocities. That's going to include the meridional flow, the differential rotation, the convective motions. You've got a source term. This is where you're going to add in new additional flux. And then you got a diffusivity here. And so if we do this, we can get just a basic, we can look at the evolution of the magnetic flux in a simpler way. And so this is a movie from HMI, and it kind of tells you what we're trying to do here. We've got an active region here that's emerged. It's being shredded off by the convective motions, being dispersed into the magnetic network, where it's being pushed around by the convective motions, the differential rotation, and the meridional flow. And so this is just a basic picture of what we want to reproduce. So if we want to do this well, we need to make sure that we're doing a good job of taking in consideration the observed surface flows. And we need to do a good job of making sure that we're bringing in the observed magnetic fields. And ideally, if we're taking the observed flows and the observed fields and we're advecting them this way, then we should come out with something that can produce flux maps of the entire sun. It should be able to reproduce magnetic butterfly diagram. It should be able to reproduce active region evolution. And ultimately, it should be able to reproduce the evolution of the polar magnetic fields. So in this model, we're going to measure the differential rotation and the meridional flow. We're going to measure convection. We're going to do an explicit simulation of the convective motions. Typically, in Dynamo models, this has been parameterized with that diffusivity coefficient. But since we're looking at a very simple case, purely at the surface, we can create a simulation of what the convection looks like at the surface. And here we can see what that simulation looks like. These are the observations, Doppler observations with MDI, and this is what our simulation looks like. And you can see that qualitatively, they're indistinguishable. Quantitatively, the convective cells are going to have lifetimes and velocities that are representative of what we observe on the sun. So how about, and so we can bring in the observed flows. That's good. So how about the observed magnetic field? Well, we want to make sure that we get the history right. And the best way to get the history right is through a process called data assimilation. Have you guys heard of data assimilation? Do you know what data assimilation is? Yeah? What's data assimilation? Yeah. Exactly. And you guys have seen this. The way that you've seen this is all of your weather observation, or all your weather forecasts. All of your weather forecasts use the data assimilation process. They take their models, they run it forward, they look at what the observations say, and they correct their model based on these observations. And so this is a way of basically converging to reality and bringing, getting an answer that is going to be as close, provide the closest contact with the observations as possible. So we can do this for the history. We can assimilate magnetograms from the sun, do a data assimilation process to make sure that we have the active region evolution in the past correct. Going forward, if we're going to make a prediction, we have to make some assumptions about what active regions are going to continue to emerge, because if we just halt active region emergence, then all of that flux at the low latitudes is going to be transported poleward, and we don't necessarily want that, because we want continued emergence to continue that cancellation of that leading polarity flux. So we need to make sure that we're bringing in some simulated active regions. And if we put all these together, get something that looks like this. A simulation from our flux transport model that I've done with David Hathaway called the Advective Flux Transport Model, or AFT. You see inside of the box, this is where the data assimilation is occurring. You're bringing in the magnetic observations. Outside of the box is where the model is just running with the observed flows that you've provided. You see that there's a good match. When the box comes around, the active regions tend to be in roughly the same place and kind of have the fragmented structure that you would expect them to see. Sure. Yeah, so inside the box, inside this area is where the data assimilation is occurring. Outside, this is where you're just letting the model run independently of the observation. So it's just taking whatever you've given it and solve that induction equation with the velocity field that you've provided. Okay? But even this isn't going to be perfect, so we have to recognize where our limitations lie. And so there are some stochastic effects that still come into play, and even in a surface flux transport model. Where are some places that we might have some stochastic effects still coming into play? Ideas? Turbulence, convective motions, yeah, absolutely. Anything else? Again, in the past, we've got the past nailed down, so we're really looking at the future, the prediction aspect. Where are the stochastic effects in there? And the places that we'll see stochastic effects coming in there is when we simulate the continued active region emergence in the future. You know, we got to put in some kind of Joy's law tilt. We don't know what active regions are going to emerge in the future. We don't know what Joy's law tilt, so we kind of have to make some approximation there. This can cause some fluctuations in our model. As you mentioned, the convective pattern, the placement of the convective pattern causes some stochastic effects. Even the meridional flow that we choose. You know, we're starting to have a better understanding of what the meridional flow looks like and how it behaves. But if we don't get this right, we might have some variability in our prediction. So let's take a look at a couple of those real quick. Active region sources. So what we can do for active region sources is we know that, you know, cycles tend to behave similarly. If you've got a very strong cycle, you're going to have this very fast rise and a very slow decay, as you mentioned. Weaker cycles are a little bit different. They're kind of a little more squished and a little bit more symmetric here. So we can use previous solar cycle data to simulate the rest of our solar cycle 24. Here we can see cycle 23 makes a good, or cycle 17 makes a good proxy for cycle 20. Cycle 17 makes a good proxy for cycle 23. Cycle 24, we're actually closer to about here at this point. And so if we're simulating all of this stuff, we can just bring in this part, this little tail in to get the rest of the cycle. And so that placement of the active regions, well, that'll give us the placement. It still doesn't give us the tilt necessarily because there's a lot of variability there, but it kind of helps reduce our stochastic noise there. But also, as you mentioned, there's the convection. And so this is a simulation that we did many years ago where we tried to simulate the evolution of solar cycle 23. And again, we used solar cycle 17 because that makes a good proxy for solar cycle 23. And we found something really interesting. So these different colors are different convective realizations. So it's just a different convective pattern. It's, quantitatively, it's the same, has the same properties, but the placement of the convection cells or the specifics of the convective cells is slightly different between each of these realizations. And we find something really interesting. What we find is that, you know, at solar cycle minimum, there's not really much change due to the stochastic effects from the convection cells. But at solar cycle maximum, when we're trying to reverse that axial dipole, we see there's a lot of variability here. So why is this? Why did the stochastic effects of the convection cells have a bigger impact on the surface flux transport model at solar cycle maximum than they do at cycle minimum? Guesses?